on YouTube. Last episode, we built a pretty printer for our abstract syntax tree that we've defined so far. And this is the output it produces, which looks pretty neat. And we're using the Dodo printer library for that in PureScript. So now that we have done that and we are able to, we have the tools we need to debug this stuff, I think the next step is actually to take this AST and get back to what the series is about initially and compile this thing into WebAssembly. So if we remember from a couple of series ago, 7 episodes ago, we had this thing where we rendered expressions into, where we compiled expressions of this form into WebAssembly. And we had this like little bit of a weird convoluted setup here. So that we could have some bindings. But now we have an AST that does a lot of this stuff more neat. And I would like us to get to a point where we can compile our little Fibonacci program to WebAssembly. So we've got lots to do, but I think we should try doing that anyway. All right. So let's make our compiler no longer do any of this. I think we don't need any of this. Just going to delete all of it. I'm going to delete all of it apart from Wasm Builder and Wasm Syntax because I'm pretty sure that we're going to need those. And I already know that we're going to use the AST. And I'm going to call that one AST because, well, we're going to have two ASTs here, right? We're going to have the syntax one from WebAssembly, and we're going to have our syntax from the source level. So that's the AST. And, well, that might be a bit of an annoyingly long prefix, but we'll see about that. I'm just going to leave it at that for now. So what's the entry point we really want? So we want the function that says compile funcs, and it's going to take an array of functions of, I'm going to hard code it to string for now. It's going to take an array of functions and it's going to turn it into a WebAssembly module. And I'm going to start out by saying that this just compiles to the empty module, just to make sure we are back to a compiling place. Okay. And as previously, we're going to be using the little builder API we built ourselves to do this. So now, I'm just going to grab our little program from main. We don't need the bit above. We're just going to use this bit, I think. So we have a few things in here that we haven't compiled before. Most notably function calls, of course, but we also haven't built if statements so far, or if expressions. So there are a few things we need to think about here. So we could go at this top down and look at how to compile a function first, and then figure out how do we compile declarations, and then go all the way down to how we compile expressions. And I think that's actually going to be the best strategy here. So my goal is to take every one of these functions that is defined here and compile it to a WebAssembly function. And we're going to create an export just for a function called main. So we're going to expect the user to provide a function called main for us. And well, if they don't, they're going to get an error somehow. All right, so let's try that. And we're just going to create a bunch of, we're just going to start by defining a bunch of empty functions, essentially. So let's use our builder. And I think there's a function here, which is like build. And this is the one that explodes if something goes wrong. That seems good to me. Exploding is all good with me. So we're going to use a bunch of stuff from the builder. So what do we have? We can declare funcs, right? That's really the main thing we want to be doing here. So we want to declare a function a bunch of times. So I'm going to say compile func, right? And this is a function that operates, so it takes a func, an AST_func string, and it returns a builder thing. And I think, oh, we did not import that yet. Actually, let's define ourselves a builder here. So builder, in our case, is going to be builder.builder. And the first parameter is the type of identifiers that we will be working with. And for now, we're just going to be working with strings here. So that's what we're going to do. So if we compile a func, I'm just going to assume that this does not return anything, which might be wrong or right. We'll figure it out. So this is a func, and it has a name and a params and a body. Okay, so right now we can just make this pure units. Just make sure everything compiles. Does not, because this needs to be ast.func. Okay, so declare func. That's not actually what we're going to do. We're just going to call compile func on all of the functions, right? So let's just do that. We're just going to traverse and throw away all the resulting values because they're just a bunch of units, like so. Okay. And we might, in order to test this out again, we're going to go back into main, and we're going to build a little pipeline up here. So before, we did the thing where we had just this hard-coded test module. What we're going to do now is we're going to say, well, we're going to compile a bunch of funcs, and those funcs are actually going to be the funcs we just parsed, right? And that's only going to happen in this case. And we no longer need to print those. Okay. And so what about run Wasm? Oh, the indentation is messed up. That's what. Okay. So this thing, when run, should now produce a file bytes.wasm, an empty one, ideally, because we are not doing anything yet. And it explodes because we don't have a main export that is called main. That is right. Hello, Ramisa. How's it going? Hope you're doing well. So one thing we're going to need to do is here, we're going to need to declare an export. So after we're done with all of these funcs, we're going to declare an export. And we're going to export main as main, I think. Okay, so let's try this one out. This time around, I'm expecting a different error. I'm expecting it to crash because the name main was not defined as a function. And there we go. It says undeclared function call main. So that's good. One thing we're going to run into, and let's just try. We'll see. We'll run into this real quickly. Are you using C#? No, this is PureScript. It's very different from C#, as you can probably tell from the syntax. Right, this is a functional language. All right, so really compiling the function is going to be declare func. And so what do we need to do? So if we want to declare a function, there's step one. So we need a bunch of parameters, right? Step one is the name. We're just going to use the name the user has used so far. And then we need a func type. Okay, so what's the func type? Well, the func type is, well, that's interesting. We're gonna make it so every function returns a number. Yeah, we're gonna do that. So what is this? This is arguments, and that's array.replicate, I think. So we're gonna replicate the arguments like this, and I'm gonna talk about what that means in a second. Right. So what does this thing do? We're gonna have as many arguments as the function takes parameters here, and because the only type we're dealing with for now is i32s, we're just going to make all of them i32s. And then, as I said, the results, we're just going to always return a single i32 here. So what I've been doing, so I'm building a compiler to WebAssembly, and what we have done so far is defined ourselves a little language, which you can see over here. This is the kind of language we can parse, and what we're doing right now is compiling it to WebAssembly. And for that right now, we're looking at how to declare individual functions. Right. So, so declare func takes, well, that's actually going to return ourselves a function here, which is the fill function. And then we're going to call this fill function. And for this thing, we need to compile the expression. And that's the body, but wait, the expression, it's not actually an expression, right? It's a list of declarations. I'm just going to say compile body here, which we haven't defined yet. So let's do that one next. So if we were to compile a body, what do we get? We get declarations, an array of those. And we need to produce a bunch of instructions, right? So array of instr, I guess. Instruction, actually. And we're just going to start by always returning the empty instructions. Oh, these are names, so that's a string. And this is a pure. So what do you not like about this thing? So this thing returns, wait, what? Oh, we need to do the number of locals. Okay, so we need to figure out how to deal with locals. I'm not going to do that right now, but we will in a second. What do you not like? What exactly is the body? I'm not quite sure what this does not like. Look at declare func one more time. So it takes an expression to a builder of unit. And I'm pretty sure that an expression is just an array of instructions. Oh, right, we need to bind this in there. Because while compiling the body, we're going to do stuff that looks up things in the environment. Okay, cool. So let's try one time. Okay, so now we're starting to get type errors, so this is good. We are producing a module here, and I think we might have some Wasm dump stuff left here. So I think it's called Wasm dump, obj dump, this one, on the bytes.wasm file, and I think we had a couple of flags. So what do we want? We want, just give me the details. Okay, here we go. So we have functions of different types. Those are nice. We have a bunch of functions, and one of them is exported as main. That's right. And then the code for all of these is just empty, because we're not declaring any yet. And then, of course, that does not match the type that these things are actually supposed to produce. So, can we make them all return something here? So what if I said i32 dot, do we have a const function? i32 const 10. Make it 42. Just gonna make the s prefix like so. Okay, so now this should work out type-wise at least, I think. Let's try that. Oh, and you can probably not see this. I'll move it up in a second. Okay, so let's try that one again. Okay, so the first thing we see is now these type check because they all return in i32 as they're supposed to, and the result of the whole thing is, well, 42, because when we call main, it just puts a constant 42 on the stack. But one thing we're not seeing here is the actual code. So I think that's -d, so it disassembles the code as well. There we go. This is the disassembly, and as we can see, all of these functions. Oh wait, again, Oh, you can see this. Okay, this is good. I might need to move my head around here. It's kind of in the way. Anyway. Okay. So we've got 3 functions and they're all just constantly returning 42, which is not surprising because we haven't actually implemented the compiling bit yet. Now, one thing I can tell that is going wrong here, without going any further, is that we're declaring the function and immediately trying to fill it. Now, if we were to do something recursively or have functions call themselves recursively mutually, well, that's not going to work. So we're going to have to do something a little different here. So we can declare these funcs, and well, the builder also has a declare func, so we need to be a little bit careful about these. So, and this is this. So if we write it like this, right? So I'm going to say not compile func but declare func here. And this is actually just going to return this fill. So this, what does this return? It's going to return a function that takes an expr, which is a syntax thing, and it returns a builder unit, I think. Does that work? Okay, so that type checks. And what it's actually going to take is it returns a function that takes an expr to build a unit. Okay, so this is what it's going to return, right? So this is the function that fills the thing, that fills this function. And then we're also just going to bundle it up with the actual function because I already know we need that. So I'm just going to say we're also going to have a func of string in here. Right, so let's just write that down so it fits. So what's going on here? And this looks weird, so damn it. Let's just indent this properly, like so. So we're going to return this thing, which is the fill function. And then we're going to just bundle that up with the function because we're going to need both of these to actually implement the function, right? Then we just need to put a pure here, like so. Now the last thing that is kind of wrong here, or that is definitely wrong here, is that we need some locals. And the locals are, we need to, for the locals, well, you know what? I'm wondering if we should, do that. We're going to do that later. We're not going to do that for now. I'm just not going to write let bindings, and we're just going to compile without them for now. And then once we need them, I'm going to get into that. So we don't need the let binding here, really. We can just go like this for now. All right, cool. So why did we do this? Well, now what we'll have is a bunch of these, right? So we're going to have declared all the functions, and now we can actually go ahead and implement them. So that's what we're going to do. We're going to say now we're actually going to traverse the fills with impl_func. Okay, and this is what is going to fill out the bodies of these. So this call is called impl_func, and it's going to take one of these as its first argument, right? And it's going to return us a builder unit, I'm assuming. So let's just go with that for now. And for now, it's just going to do exactly what we did before. So it's just going to fill like this. I'm just going to type out these things because we're going to need most of them, I'm assuming. Probably don't need the name anymore, actually. The params we're probably going to need. And then we're just going to fill it with, as we did before, an i32 const. Oh, we can just say compile body, I guess. This is what we had before, right? But the important bit is that the sequencing is right now, because we declare stuff before we go ahead and implement, and now this means that now we can access functions independent of the order in which they're defined, and we can also do recursive stuff. So this was kind of important, and I decided to do this refactoring now rather than later when we've written more code that is going to make it a little harder to follow what's going on there. I'm assuming this is hard enough to follow already. Okay, so if at any point you have a question or you don't understand what's going on, please feel free to ask right away. I'm happy to answer any questions you have. So now we don't need this compile function anymore, right? Because we now have declare func and impl func. We've split it into two. All right, cool. So when we compile the body, we do need something a bit different, because we're going to need a little bit more than just the declarations. What we also need is to know, if you give me a name, a function that takes a string to an int. So what does this mean? This is find local, really. So when we compile the body, we need a function that when we find a variable, we're going to need to be able to look that variable up. And it's most likely, it's going to be either a parameter or a locally defined let thing. Does that work? No, it does not. So this is not find local, this is find param, right? So yeah, that's gonna be weird. Yeah, that's a little weird. Our DSL doesn't really handle this yet. Let's just do it like this for now, and then we'll find out if that works. Okay, so this is going to be easy to implement for now. We're just going to say find index params as the function we're passing in here. Okay, we need to say we need to find index like so. Find index, and then is there an element index? Okay, that's the one I want. Now this is failing because this is a maybe. I'm just gonna say from just for now, and we'll deal with the failures later. Really, if this failure appears, that's a problem in the program, but we need to report it, of course. But for now, that's good enough for me. Okay, so now let's get to compiling the body. So there's a bunch of declarations here. I'm going to say something horribly unsafe. I'm going to say the only thing we can compile right now is if we have a single declaration. And I'm going to say in any other case, I'm just going to crash and say multiple declarations not supported. Okay. And if we have a single declaration, we're just going to do the same thing we did before. And here we say case decals of. Okay. So let's see what happens here. This should crash now because our main function or Fibonacci function actually has two declarations in there. And there we go, multiple decals not supported. So let's go in and change that for now. So as I said, we're not doing let bindings just now. So I'm just going to hard code this. We go, that works. And now let's actually be more specific. So the only thing we can deal with right now is a single expr declaration. Okay. And then we're going to say, well, I actually want to compile the expression. And I'm going to pass the find param down there. So what does compile expression do? So this is going to accept the same function, string change, like this. And then it's going to accept an ast.expr of string. And it's going to return an array of instructions again. Right? But now we're finally down to a single expression. So this is where we can start pattern matching and compile, like creating actual code. So we have a bunch of different expression types. So let's write those first. And I'm going to say, for now, I'm just going to compile all of these to just an empty array of instructions. So this is expr, as you can tell. So what do we have? Some of these are easy, some of these are harder. Okay. So if we have an intlet, this is really easy because we're just going to say, well, that's actually an i32 const of that value. And if we have a boolet, well, this is a boolean, right? So I'm just going to say that. So if that's true, then we're going to say 1. Otherwise, this is going to be 0. So we're saying booleans are represented as i32s, and 0 is the boolean false, and 1 is the boolean true. Okay. So if we have a variable name, things get a little more interesting. This means we need to get the value of a local. So we're going to call local get, and then we need an index. And luckily we have a function that gives us that index. So this is actually a local index, which I should probably say in this type signature to make it a little clear what's going on. Okay. And we need to pass that expression down. Okay. And we're not doing any of the others yet, but do we have something in main that should be compiled now? No, but if I made this thing just say 42, I think we should see something in add. So this is add, right? Yes, we're outputting the constant 42. Now, one thing I want to check is if I say y, does it look up a local 1? It does. So that's exactly what it needs to do here. Right, cool. So looks like we're cooking with gas. In our compiler, the next thing we're going to do is compile binary operations. So we have an op here, and we have 2 expressions. So E1 and E2, or left and right maybe. So what are we going to do? Well, we're going to compile the left one, then we're going to compile the right one. Right, and then we're going to compile the operator, and let's write that function. And if that seems confusing to you, I'll talk to you about that in a second. So this is and that's not actually how it's going to go. So this is just a single instruction, right? Every operator is just a single instruction in our case. And we need to use native here because these are actually effectful. So we're going to say, we're going to do this. So this is the left side. I think I'm allowed to shadow, probably not allowed to shadow. This is the right side. Then we're going to say, we're going to concatenate these together. So the left side on the stack, the right side on the stack, and then finish them off by invoking the operation that this operator represents. Okay, so now we need to go and say, well, what's the WebAssembly equivalent of these things? And well, luckily WebAssembly has equivalents of all of these. This is i32 add, i32 sub, i32 mul, i32 div, and we're gonna say we're using an unsigned div for now. That might be right or wrong. And let's use a signed one. No, unsigned. Let's use a signed one. So what do we have here? This is i32 less than. And we're going to use the signed one for all of these. i32 greater than signed. i32 less than equals. Less equals signed like so. i32 greater equals signed. And the last one is i32 eq. There we go. And so now, if we were to go back into our main module and turn this back into x plus y, what I expect to be able to see now is to have the function code for the add function be local get 0, local get 1 add. There we go. So that's exactly what the body says here. So we're going to put x on the stack, going to put y on the stack, and then we're going to add them together. All right, again, nothing groundbreaking here, but we're getting there. So now let's do ifs. I don't think we have looked at ifs in WebAssembly yet, so maybe we should, or we could just wing it. So step one, just compile all of these. So const prime, gonna compile the expression. We're gonna do that for the then case and for the else case. Not execute, just compile to WebAssembly. Okay. And then what are we going to do? Okay, so we're going to output a bunch of things here. So step one, we're just going to put the condition on the stack. Okay, so now the condition lies on the stack. And now we're going to add the if expression that WebAssembly provides us. So s dot, I think it's called if. Yes. So what does an if need? It needs a block type as its first argument, and the block type is always going to be an i32. How is block type defined? Is there a block type index or a val type? So it's always going to be a val type here. Okay, so we're going to say, so if expressions are a bit tricky, but we'll get there. So we're going to say the block type is always going to be an i32. So every if returns a value in our case, because we do not have statements like statement ifs that do not what's happening? Sorry, we do not have statement ifs that don't return a value, right? Or ifs are always then else, and both branches return something. So now why is this complaining? Oh, because this thing is not quite right yet. Okay, so what does an if have other than that? So it has an array of instructions and then two more. Okay, so it accepts two more array instructions. Okay, and those are the then branch and the else branch, I think. And this needs to be wrapped up in an array like so. Let's see if that works. That looks fantastic. So what do we have? So this is the code for our Fibonacci function, really. So step one, we get the value for the local 0, which is our parameter x. Then we put 2 on the stack, and we ask, is x less than 2? And if it is, we output something, a loop. So this is wrong. Okay, so we're doing something wrong in the encoder. So when we output an if, we're doing something wrong. So as you can tell up here, the loop is 0 for And the if is also saying also 0, 3. I'm assuming this is 0, 4. And we can already tell that this thing broke because there's, well, stuff we output is wrong. So this looks better. Stuff is still broken. Start arity and end arity of one-armed if must match. So the problem is we're exporting a one-armed if here, but what about the else branch? So unless array null else, so this is the else branch. I don't think that's empty. Oh, it might be empty. Because I think we're compiling those two. Right, because these things are calls. So let's call them to return a const value here for now. Let's make those 65. So calls are 65. And then we go back in here. So it's just that the encoding sucks if you have an empty, or like the encoding doesn't work if you have an empty branch. There we go. So now the other branches are 65. And this thing actually returns 65. Right, because the first value we give it in the main function here is 10. And 10 is not less than 2, so it returns the value that is in this branch. So we're this close to actually getting that. Oh, this is amazing. I love it. So now for the grand finale. This is the function and these are the arguments. How do we compile function calls? Well, it's quite easy actually. What we do is we say we're going to put all of these arguments on the stack and then we're just going to call the function at the end. Okay, so we're going to say, we're going to do folder map. We're going to compile all of these arguments. And then the only thing we need to do is at the end, and this is, does this work like, folder map's not going to work because this is going to return in a boulder, right? So we need to say, we're going to fold. Yeah, okay, so this is a little trickier. So let's do this real quick. So these are the args. I'm going to traverse them with compile expr find param. Like so. And then we're going to say, okay, now we need to fold together all of the arguments. And we're going to use array.fold here. What do you not like about this one? This needs to be a pure, of course. Like so. Yes, that works. Can you maybe run the program? I'm running it over here over and over. Right? I mean, right now it's going to return something nonsensical because WebAssembly is going to choke on it because we're putting different things on the stack, but we're not actually calling it. So the else branch here is, these are the two different arguments, right? We separate 1 from x and we subtract 2 from x. Those are these two arguments. So we're putting those in the stack. The problem is just that we need to actually call these functions now. So let's do that. And I believe our builder actually has a function for that. So let's find that. So our builder has a call func thing, which accepts a name, which is the func, and gives us the actual call instruction. So all we need to do after we're done with the args is actually append this call instruction. And I believe if we run this, we should get out a number, which is 89. Okay, I'm not sure if that's right, but we could check. So we should check what the Fibonacci of 10 is, right? So what's the Fibonacci number of 10? I just want this thing. Give me a table. So number 10 is 55. Okay, so we're doing it. Okay, so we're getting 89, which is the number 11. So we're doing something a little bit wrong here, where our definition is wrong, I guess. So if we go into main, we should say If x is less than 1? No, that's not good. I think the way it works, see, it's just fn of 0 is equal to, oh, fn of 0 is 0. Okay, so we do this. Maybe I'm being daft here, so let's think about this. I haven't implemented Fibonacci for a while. So f of 1 and f of 2 are equal to 1. Now, do we need to say 3 here for this to work? Did we just shift the indexes around, indices? So what do we get now? Now we get 55. Which, there we go. That's the 10th Fibonacci number. Perfect. So we have taken this program and we have compiled it to WebAssembly, and we're running it inside the WebAssembly engine that Node ships, and we're able to compute the Fibonacci numbers. So there's a bunch of recursion going on here. We're calling functions we've defined, and we're doing all of that with just this little piece of code over here. So I think that's great. But the one restriction we have right now is that every function body has to be a single expression. We do not allow the let bindings yet that we have, well, that we allow grammatically. But I think that is a good point to say, this is cool, and the next time around we'll look into how to do let bindings. So thanks everyone for watching, and see you next time around.